Hi Year 11, so this is the summer 2020 paper 4 that we're going to go through. You should have a paper copy, and if you don't have one yet you can grab one from Noah so that you can try and answer it as you watch this video. So let's have a look at question 1. It's a speed time graph, so it's a motion question. So it tells you about his journey, and it tells you specifically that it takes 74 minutes in total. Now, with the speed time graph, it's a kind of thing that they do to trick you, is they put the units as slightly different. So instead of kilometres per minute, they've given it as kilometres per hour, whereas the time's in minutes, and so the time values are not being measured in the same way, so you just need to be aware of that. And so part A asks you to find the total distance travelled, and we know that distance is speed multiplied by time, so it will be the area under the graph, so calculating all of these areas and adding them together. And so what I've done is found the area by these values, obviously 5 times 20 here, but that is then being divided by 60 so that I can find the speed in kilometres per minute, so that it matches the time unit, and that will then work and get me the correct answer, because I'm going to do a kilometre per minute multiplied by a minute gives me kilometres. So you add them all together and you will get a value of 17.2 kilometres. And then in part B it asks you for your average speed, and so obviously you're going to do the total distance divided by the total time. So we know that we have taken 17 kilometres to two significant figures. It doesn't matter if you put 17.2. Divide it by 74 minutes and you get a value as kilometres per minute. That isn't the unit of speed that was used. That was kilometres per hour, so I'm going to convert that into kilometres per hour. So obviously if they travel 0.23 kilometres every minute, if you multiply that by 60 minutes, you get the total distance travelled in an hour. And then that's 13.8 kilometres per hour there. Then part B asks you to state and explain which feature of a speed time graph shows acceleration. So the statement is that the gradient gives you the acceleration, and then the gradient is equal to the change in speed over time. So effectively you're getting 1 mark for the statement of the feature, that is the feature, the gradient, and then 1 mark for explaining what that gradient gives. So you're basically proving that you know what acceleration is. And then it says, state and explain the acceleration of the person at time is 40 minutes. So if we go back to our graph, at 40 minutes, which is halfway through the bus's journey, if we go up to look at the speed, at this point, the gradient at 40 minutes is completely horizontal. Okay, so it's a steady speed, and the gradient is 0, so we don't have any acceleration. So the statement bit is that the acceleration is equal to 0 metres per second squared, and the explanation is that the speed is constant. At this time, or you could say the gradient is 0. Okay, where it says explain, you always want to relate it back to the physics. Okay, so the statement bit's good to reference the graph. The explanation needs some kind of physics in your answer. So the speed being constant or the definition of acceleration there. So just be careful with that. Number 2, figure 2.1 shows a train. The total mass of the train and its passengers is given. You know its initial speed is 84 metres per second. The driver applies the brakes and the train takes 80 seconds to slow down to a speed of 42 meters per second. Calculate the impulse applied to the train as it slows down. So we know that impulse is change in momentum. That's what we mean by impulse. So that's going to be the final momentum minus the initial momentum. Okay, so you're going to do mv minus mu, okay, which is mv take u, which is going to be 750,000 multiplied by 42 minus 80. And when you do that, you are going to get a value of, let me check it on the calculator, sorry, I've just realised this 80 should be an 84. I was thinking this, I've done something wrong here. That's your time, isn't it? Not your initial speed. So just be careful there. Do a double check. Don't do what I did. And then when you do that, you're going to get a value of 3.5. 1, 2, 3, 4, 5 zeros. So 3.2 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay, and that unit that you can give can either be force times time, so Newton seconds, that would be fine, or the unit of momentum as well. So you could also have said kilogram meter per second, that would be fine. Then it asks you to calculate the average resultant force applied to the train as it slows down. So we also know that impulse is equal to force multiplied by time. So force is impulse divided by time. And we know that that then took 80 seconds. So we can take this number and then divide it by 80. And you get a value of 5. And don't forget your unit there as well. So that's the impulse calculated. Then it asks you to suggest how the shape of the train helps it to travel at high speeds. So if we have a look at the train itself, and we know that it's travelling in this direction, you can see that you've got a pointed front, okay, and so obviously what the train is meeting are lots of air molecules, and where they collide there's air resistance that then opposes the motion. But because it's been tapered, so it's got a pointed nose front, the surface area initially is very small, and so it reduces the air resistance or drag because it's more streamlined. So you can say it is streamlined to reduce air resistance. Okay. So, the train took 80 seconds to reduce its speed from 84 meters per second to 42. Explain why, with the same braking force, the train takes more than 80 seconds to reduce its speed from 42 to 0. Okay, so obviously when it is trying to slow down, it's applying its brakes, but also we know that there's air resistance opposing the motion. Okay, now when it's travelling very, very quickly, the air resistance is going to be large because it's going to be colliding with lots of air molecules in a short space of time. But as the train slows down, it's cutting through the air at a lower rate. So actually what has also happened is the air resistance decreases, and so the resultant force on the train changes, because you've got the thrust from the train itself, then you've got the braking force acting in the opposite direction, which is the same as it was before, but now the air resistance has got less, so the overall force against the train has gone down. So what you want to say is that as the train slows down, so at slower speeds, there is going to be less air resistance. Alright, last bit then. On a wet day, the train travels a greater distance before it stops along the same track. The train has the same speed of 84 metres per second before the brakes are applied. Suggest a reason for this. So why is it that travelling at the same speed, it now suddenly takes a much longer distance before the train comes to a stop? So obviously when things are wet, the friction goes down. So we know that the friction between the train wheels and the track will be smaller when they're wet. Okay, so that is number 2. Number 3 then. Okay, so let's have a look. We've got a solar panel receives energy at a rate of 5 kilowatts. So we know that that's 5,000 watts. Always helpful to convert into standard units before you start so that you don't put the wrong number into the equation. And we know that thermal energy is transferred from the solar panel to water with an efficiency of 20%. So only 20% of this 5,000 watts is transferred to the water. So we can immediately find 20% or a fifth of the 5,000 watts to know our total power rating going to the water. And so we can see that that's going to be 1,000 watts. So this is the power that we're actually dealing with to heat the water. So a cold water of mass 15 kilograms enters the solar panel every hour. The specific heat capacity of the water is given to you. It's 4,200 joules per kilogram degree Celsius. Calculate the temperature increase of the water. Okay, so we know that we are going to use a specific heat capacity equation. So Q is equal to MC delta T. And we want to find delta T, the temperature change. Okay, so I can rearrange this firstly, and delta T is equal to Q over MC. And Q stands for the heat energy supplied, but what we actually have is a power rating, and so we need to find Q, the energy, by doing the power multiplied by the time, and the time is 1 hour that we're looking at, so we need to convert that into seconds for it to work. So we've got 1,000 multiplied by 60 minutes multiplied by 60 seconds to get the total number of seconds, and that is the Q value that is being put in to the system, and then you know that in that time it's 15 kilograms, and then C is this value here. So we now have all of our values, and we should be able to find our temperature increase. So we're going to do delta T is equal to Q, which is 1,000, multiplied by 60 over M, which is the 15 kilograms, and C, which is the 4,200. And you will get a value of 57.5 0.1 degrees Celsius temperature increase there, and that is your final answer. So it's worth 4 marks. So you're going to get 1 mark for stating the equation, so do that first before you do anything else maybe. 1 mark for recognising that you need to convert the power into energy. 1 mark for recognising that you then need to multiply by 0.2 because of the efficiency, and then 1 mark for your final answer. Then it says, state and explain 1 advantage and 1 disadvantage of heating the water in a solar panel compared with heating the water in a coal-burning boiler. Now, obviously there are many advantages and disadvantages to all of the different energy resources, but the key thing to notice here is that it's asking you to make a comparison of 2 of them. So you can't just give any of the random advantages or disadvantages. You have to think about what makes one of the advantages an advantage over the other type stated. So what you can say is the advantage of using the solar panel over in a coal burning boiler is either that it's renewable, or that it's not polluting, or doesn't emit greenhouse gases, so there's no greenhouse effect. Okay, that's an advantage that a solar panel has that a coal burning boiler does not. And obviously the explanation there is either going to be coal is a non-renewable source, whereas the sun won't run out, not polluting because solar panels do not produce carbon emissions, which coal power stations do, no greenhouse effect because no gases are given off. So the one I'm going to explain is the renewable one and how to write that, because it's quite easy to explain this one. You just say a coal power station emits greenhouse gases such as carbon dioxide, whereas a solar panel does not. The renewable one, what you want to make sure you reference is that solar panels rely on the sun for their energy, which is a source that won't run out. Okay, so it's about stating the energy availability for each one. And then for your disadvantage, for solar panels, an obvious one is that you cannot use them during night time because there's no sun. Or you could say that it needs a suitable roof space that is kind of sunlight facing. But I would suggest going for the not available at night is the most obvious one. Okay, so energy cannot be produced when light levels are low. Sorry, I can't squeeze it in. I'm trying to write big for the video. And then obviously the explanation, sorry, words won't come out. The explanation is that solar panels rely on the sun. Whereas coal can be energy from coal burning can be produced at all times of day. Okay, sorry, it's very messy there. Okay, number 4 then is a thermal question. So you've got a liquid in glass thermometer without a temperature scale. It then says that the liquid inside the thermometer has a melting point of minus 39 degrees Celsius. Describe simple experiments to mark the positions of the fixed points in this liquid in glass thermometer. So the fixed points, if you can remember, are 0 degrees Celsius and 100 degrees Celsius. But the way we define these 2 points are the melting and the boiling point of pure ice, and then water for the boiling. And so you're going to need to initially place the thermometer into a beaker of melting ice. That's the first bit. Now it's really important that you use the word melting in your answer, because the fixed point is defined by this. 0 as a number is meaningless unless we attach it to something, and so it's when we know that ice is melting. So then we want to wait until the ice has all melted and the bead has stopped moving. Okay. So here you want to be careful. It's not just about waiting until all the ice has melted, because that's quite difficult to actually spot that exact moment, whereas it's much easier to notice when the thermometer value stops changing momentarily. And then what you want to do is place the thermometer above boiling water so that there's steam. Above boiling water, and again you want to wait until the bead stops moving again, so the liquid in the thermometer reaches its new highest point. Okay, and then you'll know that you've reached the 100 degree point. So you are going to get a considerable number of marks for saying this, but the thing that I haven't added yet is that we want to reference what you're going to mark. So once we've got the ice melted and the liquid in the thermometer stops, I've written melting, it should say moving, sorry, then you would mark the 0 degrees Celsius at this point, and then at the steam one, mark as 100 degrees Celsius for that one. So don't forget to reference the actual marking the positions, or otherwise you will not get the mark. So then it says underneath, a scientist is measuring temperatures at the South Pole. These have a minimum value of minus 90 degrees Celsius. State why the liquid used in the thermometer would not be suitable for this scientist. So obviously, if the melting point is minus 39, anything colder than that, the liquid's going to be in solid form, and minus 90 is definitely colder. So you just want to say that the liquid in the thermometer will actually not be liquid at this point. So the liquid will actually be in solid form at this temperature. Alright, then it asks you two ways you can design the thermometer differently. The first one is to increase the sensitivity of a liquid in glass thermometer. So the sensitivity is if the temperature changes by 1 degree Celsius, how much further up the thread will the liquid go. If it only jumps by a small amount, that's a small sensitivity. If the liquid jumps by a large amount for that temperature change, that's a high sensitivity. So what we want then is to increase the amount the liquid moves up per degree Celsius. So if we make the tube narrower, the liquid will have to travel further up for the same volume change when it expands. So what you're going to say to increase the sensitivity is you want to have a thinner tube. The technical word there is actually bore, B-O-R-E. That's one possibility. You could also have said that you could switch the liquid so that it's one that expands more when you change the temperature of it. You could also have used a smaller bulb so that it's forced up. Increase the range for part II. Obviously what that means is it wants to be able to measure temperatures of a wider range. So you know there that you could increase the total length. Sorry, I keep moving this is not helpful. One thing you could do is increase the total length, because if you think about it, once you've reached the temperature where the liquid moves to this point, any further temperature increase is not going to be visible because you're not going to be able to allow it to move up the tube. So you would just use a longer tube there, is the easiest one you can write. Always good to just have one answer ready for those so that you know what to write. Then the last bit is state the property of the liquid that ensures the scale is linear. So that means for the same jump in temperature, you get the same length increase each time. So you know it's going to constantly increase by a constant amount. So you need to make sure the liquid will expand uniformly. Okay, so what that means is that the change in volume of the liquid for every degree Celsius going up is exactly the same. The volume increase is the same there. Alright, number 5, your favourite. These diagrams I know are not ones that you particularly enjoy. So you've got crests of a wave approaching a barrier where the wave is then reflected. And you can see, here's the barrier. These are the wave fronts. This is the direction the wave is travelling in. And then it asks you to draw 3 crests of the reflected wave. I'm just going to pause the video while I do this, because otherwise you'll be sat watching me for ages, but then I'll talk you through what I've done afterwards. Okay, before I finish the diagram off, sorry, just dropping things all over the place, I've numbered the steps I've taken so that you can see what order to do things in. So step 1 is I have extended the direction of the wave travel all the way to the boundary, and that allows me then to measure the angle of incidence. So that was step 1. Step 2 was to draw the normal line, and that is at 90 degrees to the barrier. Step 3 actually involved then measuring the angle of incidence. So that's the angle between the normal and the ray, so that's 30 degrees. So then when it is reflected, angle of incidence equals angle of reflection. So I found 30 degrees. So I know that from this point the ray travels back along this line. This though is the ray direction, not the wave fronts. And so what I need to do is find 90 degrees to that direction to find the wavefront direction. So I've then found 90 degrees, marked it at step 4. So what I can do now is draw that on there. Okay, and so what's important is that every time one of these wavefronts meets the barrier, it will then bounce off so that the angle of reflection is 30 degrees, just like the angle of incidence. And so you need to make sure that you keep your ruler parallel next to the one that you've originally drawn, and then you find where other crests have met the barrier, and then you're going to draw that line on there. Okay, so you can see, again, I'll come above so you can see it. The wavelength hasn't changed, so the distance between the crests shouldn't have changed either. And so what the examiner will look for is that the distance between crests is the same as it was previously. And they want at least 3. So that's 3 there, but you can draw more, that would be absolutely fine. But that is enough in this case. But what will actually happen is they'll then travel forward like this. So that's all you need to do there. The wave has a wavelength of 36 centimetres and a speed of 1.2 meters per second. So we just need to use the wave speed equation, v equals f lambda, and we're trying to find the frequency, so we're going to rearrange. So we're going to do 1.2 meters per second for the speed, but notice that this is in centimeters, whereas this was meters per second, so we need to convert that to 0.36 meters so that they both are using the same units. Okay, so the wavelength is actually divided by 0.36. Oh, excuse me, throwing things around. And when you do that, you're going to get a frequency of 3.3 hertz. Okay, and you need to make sure you've got a unit because they aren't giving one there for you. And then part C, oh my goodness, is a fill in the gap. What a treat. An echo is the name for a reflected blank wave. And so echoes obviously come from sound. So from a reflected sound wave. The waves that form an echo are a type of longitudinal waves. Longitudinal waves are made up of blank and rarefactions. So you want to use the word compressions. Okay, so regions where the particles are really squashed up, and then rarefactions, regions on the sound wave where particles are quite far apart. So that is number 5. Okay, so another light question this time. This time you've got glass prisms inside of a box, and you're told the angles. This one's obviously 90, and then you've got 45 and 45, and then same down here, but it's been reversed round. So you've got light coming in at the top, there's a gap in the box. It reaches the first prism, and basically this light is coming from behind a wall. So we know that obviously the eye can't see from behind the wall without this. It tells you that the ray of light undergoes total internal reflection in the prisms, so that's important for you to know what to do. On the figure, complete the path of the ray through the device and show how it emerges. So, let me zoom in on the diagram a little bit. What we know is that when light moves into a new medium, it will change speed. And if it does that at an angle that's not 90, that then causes refraction and it changes direction. But at the moment, we can see that it's coming in at 90 degrees. Okay, and so although it will change speed, it won't change direction if it's coming in at 90. And so what we can do is continue that light ray all the way to the far side of the glass prism. It's going to carry on inside. Okay, but now because this barrier to go back out to the air is at an angle, I'm going to draw the normal line to the barrier at that point. We were told that it undergoes total internal reflection, and so it is reflecting within the glass prism. This is the angle of incidence. The angle of reflection is then going to be equal to that, and hopefully you can see just from like triangles, this is 45, so this will also be 45, and so it will vertically move down because it totally internally reflects. Let's see if I can get this as accurate as possible. I would suggest a protractor is probably quite a good idea, but I'm just being a bit lazy. Okay, so this angle of reflection is also equal to the angle of incidence, it's 45, but now this is going to be 90 degrees when it reaches this barrier, so it's going to carry on straight through and travel straight down. Again, this is 90 degrees, and so it'll change speed when it enters the new medium, but it'll carry on straight. But now it's hitting at an angle of 45 degrees to the far side boundary. And so I'm going to draw my normal line again. And you can see now the new angle of incidence for the total internal reflection will be 45 degrees there. And so it will come out also at an angle of 45 degrees. And it will travel out into the eye. Okay, so that is the path that you're going to draw. Then it asks you to show that the refractive index of the glass with a critical angle of 45 degrees is 1.41. This is just a simple recall question. They're asking you to remember that n, the refractive index of a medium, is equal to 1 divided by sine of the critical angle. Okay, and so you're just going to do 1 over sine 45, and when you do that, you do indeed get your 1.41. Okay, don't panic if you see your root 2, just push your SD button to get your value. And then it's been proven. Alright, number 7, on to electromagnetism. A student makes a transformer that uses an alternating current supply with an EMF of 12 volts to induce an output PD, so voltage of 2 volts. The student is provided with 2 lengths of insulated wire and a U-shaped piece of iron. Remember that iron is a soft magnetic material. Okay, so it's easily magnetised but easily demagnetized. Think about these things before you carry on. And then it asks you to complete and label figure 7.1 to show the transformer connected to the supply and the output from the transformer. So again, I'm going to pause so I can draw it so you're not having to watch me for ages, but then I will show you what I've done. Okay, so what I have added is a primary coil wrapped around the left hand side of the iron so that it has an iron core, and you can hopefully see 1, 2, 3, 4 turns, and that is connected to my 12 volt alternating current supply. And then I have a secondary coil which only has 2 turns, and that has been connected to the 2 volt output. You just need to say that it's a 2 volt output, you don't need to add a circuit in there. You're going to get marks for clearly having a primary and a secondary coil and there being a difference in the number of wires on each side. If they're the same, it's not going to be a transformer. You'll get voltages the same on both sides. So please make sure that you clearly have a different number. Then you need to label it, and it also needs to be wrapped physically around the iron. And they will be checking for all of those things. Then it asks you to explain the function of the piece of iron. So why are we having to use the iron core in the first place? Okay, so what we want to say is worth 2 marks. We need 2 points. Firstly, it will produce a stronger magnetic field inside of the secondary coil. Okay, and this will cause or enable better induction. Okay, and so you get a better induction, you get a better voltage value there. So 2 points, 2 marks. The output of the transformer is then connected to a lamp. The current in the lamp is 100 milliamps, so 100 times 10 to the minus 3 amps, and it's 100% efficient. Calculate the input current into the transformer. So we know that if the transformer is 100% efficient, the power across the primary coil will be equal to the power across the secondary coil. That's what we know. There's no power loss. Okay, and we know that P is equal to IV. So power is equal to current times voltage. So power in the primary will be current in the primary multiplied by voltage in the primary. So IP VP must be equal to IS VS. Current in the secondary, voltage in the secondary, because the products have to be the same. So we already know that we want to find IP. We're told that the voltage across the primary is 12. The current across the secondary, because the lamp is connected to the output, which is the secondary, is going to be 100 times 10 to the minus 3 multiplied by 2, because that's my output voltage. Okay, so I can then say that IP is equal to 100 times 10 to the minus 3 over times 2 over 12. Okay, I'm just rearranging this to get my equation. And when you do that, you are going to get a value of 0.016666 amps. So 0.017 amps when you then round that. And that's your value there. The last part of the question says that we use another transformer in a school lab. It's stepping it down, and you have a main supply with a potential difference of 110 to 12 volts. Oh, I should also point out, I just thought about this, sorry. The reason why you know there should be more on the primary than the secondary is you originally have 12 and you go to 2. So it is stepping the voltage down. So this should have less on this side. That's just made me think of that. The transformer is mounted in a metal case. State and explain an essential safety feature for this arrangement. Okay, so we know that if it's in a metal case, that's a big clue. Metals conduct electricity, that could be quite dangerous. If there's a problem with the transformer and then you touch the metal case, you could get a really nasty electric shock. So we need an alternative pathway for the current if it breaks. And so it needs to be earthed, it needs to be connected to earth. So statement, connect the case to earth. That's 1 mark. And then your explanation is why you need to do that. And you just need to say one of the reasons why it might then cause an electric shock. So you can say if the insulation fails or if the live wire inside touches the case. I'm sure you can hear the pigeons above me. So if the live wire touches, that means that current will flow through the metal case. That's why you then need to connect it to earth. Ooh, lots of talking. Right, number 8. This is electronics, so again it's for triple only. A light emitting diode, LED, is a diode that emits light when there is a current in it. Draw a circuit diagram showing an LED connected so that it is lit in series with a battery and a fixed resistor. Use standard electricity symbols. Worth 4 marks, so quite a solid question there. I'm just going to pause again while I draw it and then I will explain. Alright, so you get 1 mark for each circuit symbol being correct. So obviously a battery is 2 cells. Your LED should be a diode with 2 arrows to show the light being emitted, and then a fixed resistor is just a rectangle. They should just be in series, so it should be a complete loop. And then the 4th mark comes from this diode being placed in the right way. So recognising that it wouldn't be placed like this in my diagram. You might have arranged yours slightly different, that's absolutely fine. It just needs to be, obviously this is your positive terminal, this is your negative terminal. Conventional current is going to go from positive round to negative, and it has to be that your diode is pointing in the same direction as your conventional current flow for your 4th mark there. So then it says the potential difference across the LED is 3.1 volts, so across here, and the current is 0.03 amps, that's I. The value of the resistance, so you're just doing resistance is equal to voltage divided by current, and you're just going to do 3.1 over 0.03 for your value, and you should get a resistance of 103 ohms, or 100 ohms if you want to round it, that's absolutely fine. Don't forget the unit as well, it's not given to you. Then you see a new circuit, you can see an alternating current power supply that has 10.5 volts EMF value that it's supplying. The voltage across the lamp is 2.1 volts and the current in the lamp is 1.5 amps. So it asks for a couple of things. It asks for the resistance of the heater and the power of the heater. So hopefully you can still see it clearly enough when I zoom out. Let's start with the resistance of the heater. So the first thing you just need to work out is the voltage across the heater. This is the heater here. It's going to be 10.5 minus 2.1. Okay, that's important there. So that is going to be 8.4 volts, so that what's gained across the power supply is then lost across the components before the charge moves back to the power supply. And now, because we also know the current entering the lamp is 1.5 amps, and it is a series circuit, the current is the same everywhere in that circuit, and so you have the current going through the heater as well. So R is B divided by I, and just so I'm very, very clear, the voltage is calculated from the difference between the EMF and the voltage across the lamp, so that you find the voltage across the heater, and then the current is the same everywhere. And when you do that, you get a value of 5.6 ohms there. And then the power of the heater is just P is equal to IV. Power is equal to current times voltage. So it's the same current as before, 1.5 amps, and this time you're multiplying it by the voltage, which was 8.4, and when you do that, you get, should really be able to see this in my head, 12.6 watts. Don't forget your unit again. Okay, a couple more questions. I think there's 2 more questions to go. Sorry, this is a very long video. So it's logic gates, so again it's electronics, it's only for triple students. Complete the truth table for a Nand gate. So I'm going to draw it out first just to help explain it. Okay, so obviously if you are asked to just draw the circuit symbol for a Nand gate, you would just draw it straight away as the full symbol, but I've broken it down into the and then the not gate. So these are your inputs. This is input 1, this is input 2, and this bit here is your output. Okay, so let's look at how this works. If both inputs are 0, and you know you need to have both of them being 1 to get an output of 1, you know that zeros will lead to a 0 here for the first one. And we know then that a not converts whatever you have going into it. So if this is a 0, then this will be a 1. So the output here is going to be a 1. Okay, let's look at the next one. 0 and 1. Well, we don't have both of them being 1s, so again that's going to be a 0. So this will be a 1. Same here, doesn't matter which way around they are. We don't have both of them being 1s. 0 gets converted to a 1. And then 1s get converted to a 1 because both are 1s. And that then is converted back to a 0. And so that is how you complete your truth table first. Then in part B, you've got a setup of some different gates, X and Y, but you don't know what they are yet. So you can see you've got some junctions, and what this means is that whatever input A is, it sends to this one, but it also sends to this one. And whatever input B is, so 1 or 0, it will input to this logic gate, but it will also input to this logic gate. Okay, and then you've got a partially completed truth table for this circuit. From the table, deduce the name of logic gate Y. Okay, so I've just labelled the inputs of Y with what they are. So I know that B connects to the top input and A connects to the bottom input. So what we are looking at is how A and B combine to make D. Okay, so we can see that when we have 2 zeros, we get a 0. When we have 0 or a 1, we get 0. When we have a 1 or a 0, we get 0, and then a 1 and a 1 makes 1. So you can see that the only way the output of Y becomes a 1 is if both of the inputs are a 1. So that must mean it is an AND gate. Okay, I need both 1s to make a 1 output. On all of the others I have zeros and I get an output of 0. So then it asks you to complete the truth table in 9.2. So what we know now is that this is an AND gate, and we can now work out what the X gate is. So we can see that A and B are inputs to X, giving an output C. So you can hopefully see that the output of gate X is nearly always a 1. And the only time it's a 0 is when both are zeros. So when either or are 1, the output is 1. So we've got an AND gate for Y, but we've now got an OR gate for X, and we know that X is the same, so this is also an OR gate. Okay, so what we then need to look at is inputs C and D, okay, going into the OR gate. So we take the truth table, and we know that if we have either C or D as a 1, because it's an OR gate, E will then be also a 1. So you should have 0 for the top one, because we don't have any 1s in C or D, but you should have 1 for this one, because you've got a 1 here, and then both these two also contain 1s. So on the mark scheme you would have got 1 mark for these two being correct, and then 1 mark for these two being correct. But hopefully that makes sense. And then the last bit of this question says, there is a current of 3 amps in a copper wire. Calculate how many electrons pass through the copper wire every 60 seconds. And the charge on an electron is 1.6 times 10 to the minus 19 coulombs. So we know that Q is equal to IT. Okay, so the total charge moving past a point is equal to the current multiplied by the time. So we're going to do 3 amps multiplied by 60 seconds. So I know that the total charge moving past a point in 60 seconds is 180 coulombs. Okay, and that is made up of a lot of electrons, each worth 1.6 times 10 to the minus 19. And so I know that I can then work out the total number of electrons just by dividing my value. And when I do that, I'm going to get a very big number. And I get 1.1 times 10 to the 21. Okay, and that is just a number of electrons. It's a number, it doesn't have a unit. Oh, we're finally on to the last question. Okay, question 10. What have we got here? A radioactive source. It's emitting alpha, beta and gamma. There's a strong field between the north and south pole. So we know that field lines travel from north to south, so we know that the field direction is straight down vertically. The lead cylinder has a narrow central hole. State and explain the effect of the lead cylinder. And so what we know is we've got this source here that is emitting alpha, beta and gamma. Radioactive sources emit in all directions, right? So there is alpha, beta and gamma going off in all directions. But because of this lead tube, which we know will absorb a lot of the radioactivity, it means that only the stuff that's travelling through the hole can get into the vacuum tube. So the state and explain, so the state is say what happens. What happens is radiation can only travel in one direction in a narrow beam. Okay, and then the explain is because the lead absorbs radiation travelling in other directions. Okay. So we say that the only thing that can go through is straight, because anything that's travelling at an angle will actually just be absorbed by the lead. Describe the paths of the alpha particles, beta particles and gamma rays as they pass through the magnetic field. So this hopefully makes you think, okay, well I need to look at my left hand rule. So we'll take alpha particles first. We know that alpha particles are helium nuclei, so they are positive. And you have to explain your answer as well, so it's worth pointing this out. So we know that the direction that they travel in is the current direction. Okay, so the beam direction is equivalent to the current direction. And now I'm going to use my left hand rule to work it out. So the field, which is my first finger, needs to point down the page, okay? And my middle finger is going to point in the same direction as the beam, so to the left. Hopefully you can see my thumb is coming up towards the camera, it's coming out of the page. Okay, so the alpha particle...
I didn't find any matching places.
Sorry, phone's going crazy. The alpha particle moves out of the page. And that should be enough there. Then for beta, what we're going to say is that because a beta particle is an electron, so the beam travelling to the left is actually equivalent to current flow to the right. So that's the explanation before I've even done it. Now, I should know that I then am just going to flip the direction that I put in part I, but I'll show you with the left hand. It's always good to have a reminder. So for the beta particle, the current direction is now to the right. It's moving to the left, but we flip it because it's negatively charged. So what we have this time is field still pointing downwards, but current is now going to the right. My hand is going to struggle to do this on the screen. So my first finger, oh crikey, let's see if I can do this in a nicer way. My first finger, sorry for it being wonky, is going down the screen. Let me see if I can rotate my camera. My middle finger is going to go to the right, and now you can hopefully see that my thumb, which is over here, is pointing down into the page. So we say the beta particle moves into the page. Okay, and then last but not least are the gamma rays, and so we say the path is undeflected. Okay, describe the path of the gamma ray. The gamma rays are undeflected by the field. Okay, and we say this is because they have no mass or charge. Alright, there we go. We are finally through the paper. Oh, hopefully that was helpful.